Hey there! Today we will implement a paper called PonderNet, Learning to Ponder. First of all credits go to the authors for writing this paper, and I hope I will be able to convey at least some of its ideas in this video. Anyway, as far as I know, there is no official implementation around, and therefore I decided to look for unofficial ones. What you see on the screen is an implementation created by the LabML people. If you're not familiar with this site, you should definitely check it out since it has really brilliant implementations of relevant deep learning papers together with annotations. The implementation in this video is very much based on their code plus some minor modifications. Anyway, I will try to give you a quick conceptual summary of the paper in a couple of seconds. However, I would more than encourage you to check out this amazing website. You can find all the relevant links in the description. Okay, now I will try to explain very briefly what PonderNet is about by going through different sections of the paper. PonderNet, in the most general sense, is a novel architecture for neural networks that can be used on any supervised learning problem. The most important feature of the PonderNet is that it can dynamically modify its forward pass. Specifically, if it thinks that a given sample is simple, it is going to make the forward pass shorter. However, if it comes across a harder sample, it can decide to make the forward pass longer so that it has enough resources to make the right prediction. This is very different from standard neural networks that have exactly the same forward pass no matter the input difficulty. So now the big question is, how exactly does this PonderNet decide on the size of its forward pass? The essential ingredient here is a so-called step function. This step function inputs two objects, the feature vector and a hidden state, and then it outputs three objects. The first one is the prediction y hat. The second thing it outputs is a new hidden state, and finally it also outputs a halting probability lambda, which is a number between 0 and 1. And after each step we use this lambda to determine whether we want to halt or whether we want to continue the forward pass. So to explain it in plain words, this step function outputs a prediction y hat, and to this end it is equivalent to standard neural networks. However, additionally, it also outputs a lambda, which enables the network to encode whether it is happy about its current prediction. When the lambda is high, we think that the current prediction is really good and there is no reason to continue. If, on the other hand, the lambda is low, we are not happy about the prediction and we want to continue, which means to rerun the step function. And this is where the hidden state comes in because it holds all the knowledge we learned in the previous steps. Okay, now that we understand the forward pass that can be dynamically stopped after any step, how do we actually train a network like this? Well, at training time, no halting takes place, and we always run the step function for a fixed number of steps. As we run the forward pass, we just collect the predictions and the halting probabilities after each step. And once we are done with the forward pass, we take all the first step halting probabilities we collected and we put them together in a way that they define a probability distribution called P, and that has the following form. This probability distribution encodes the probability that our forward pass halts after a specific number of steps. And if you're wondering why we should care about this distribution, well, it is used inside of the loss function. So the loss function is composed of two components. The first component is the reconstruction loss. This reconstruction loss is very similar to standard supervised learning losses like the mean squared error for regression or cross entropy for classification. However, there is a twist. We don't just take the prediction of the last step, and instead we take all the predictions after all the steps, and then we compare it with the ground truth using, let's say, mean squared error, and finally we compute a weighted average over all steps. And not surprisingly, the weights are nothing else than the probability distribution P. In simple terms, you want to give more weights to steps where the halting is very likely, and low weight to steps where it is unlikely for the network to halt. The second component of the overall loss is a so-called regularization loss, And again, it has to do with our predicted probability distribution. The goal of this component is to force our network to halt after the fewest steps possible. The way it is done is via forcing our predicted distribution to be similar to another fixed distribution. Namely, we want our P to be as similar to the geometric distribution as possible. If you're wondering why geometric distribution, well, it is because the probability mass function of the geometric distribution is decreasing. That means that the most likely halting step is actually the first one, and each consecutive step is less and less likely. Standard way of enforcing two probability distributions to be similar is to use the KL divergence. Anyway, to summarize, the reconstruction laws make sure that the predictions are close to the ground truth after each step, and the regularization laws make sure that for most samples, the network does not take too many steps. However, it also encourages the network to take more steps when really necessary. Finally, at inference time, we don't need this probability distribution P anymore. And if the network thinks that it has a good enough prediction, we let it hold before reaching the maximum number of steps. And this, of course, makes the computation way more efficient. All right, so let us start with the implementation. First of all, we will create a util script. Okay, let's start with the dataset. In the paper, one of the datasets the authors test the PonderNet on is called the Parity dataset, and it is a binary classification dataset where the features are vectors with 3 possible entries, 0, -1, and 1, and the target is nothing else than the parity of this vector. So first of all, we can specify the number of samples we want to have, and note that we will actually generate this data set on the fly for each sample, so number of samples can be more or less anything. Number of elements is a very important parameter because it represents the number of elements in the input feature vector. And finally, we can specify the minimum and the maximum number of non-zero elements. And the reason why we want to do this is to control the difficulty of the problem. Here we just handle the case where the user did not specify a custom range. And here we just run a sanity check on the specified range. The length of the dataset is nothing else than the number of samples that we chose. Okay, and now we want to generate a vector of zeros, -1s, and 1s, and then we want to compute its parity because this parity will serve as the target. And just for the record, we are not going to guarantee reproducibility. It means that if we access the same index of the dataset twice, very likely we will get a different feature vector and a different parity target. We start by pre-populating an empty vector of zeros that has the size of number of elements. And here we randomly sample an integer which will represent the number of non-zero elements that are going to be inside of our feature vector. And for this, we are using the range that we defined in the constructor. And then we populate the first n non-zero elements of the vector with -1s and 1s. And here we just randomly shuffle the elements of our feature vector because we don't want all the -1s and 1s to lie at the beginning, but we want them to be randomly spread out across the entire vector. And that's it for our feature vector. And now we just need to compute the parity of this vector. We count up the number of 1s inside of our feature vector. And if the number is divisible by 2, then the parity is 0. Otherwise, it is 1. And finally, we return our feature vector and our target. Let us test out what we just implemented. First of all, let's not restrict the number of non-zero elements in any way. And the values of these elements are zeros, 1s, and -1s. And if you just count up the number of 1s, you should get 2, which is divisible by 2. Or in other words, there is an even number of 1s, and therefore the parity is 0. As mentioned before, the fact that we're accessing a 0 or first sample doesn't really mean anything. There is randomness and we don't get the same result. Anyway, here there is 0 1s, which means that the parity is again 0. Here, interestingly, all of the elements are either -1 or 1. It seems like there are 5 ones, which means that the parity is 1. And yeah, here we have 3 ones, again, parity is 1. If we just focus on the number of non-zero elements, which means either ones or -1s, we can see that the first query had 4 of them, the second one had 3 of them, the third one, interestingly, had all elements non-zero, and the most recent query had 5 elements that were non-zero. And now we can instantiate another dataset where we actually specify the range. And now if you implemented everything correctly, the number of non-zero elements should be between 1 and 3 inclusive. Here we have 2 non-zero elements. Here we have 1 non-zero element. Here we have 3 non-zero elements. 1, -1. 1. Anyway, it seems to work. And again, the way I think about this is that the more non-zero elements you have, the harder the problem is, right? Intuitively, if we take the extreme case when all the elements are 0, then clearly the parity is 0. The other extreme is that there are no non-zero elements, which means everything is either -1 and 1. And this would take some effort to actually go through and determine the parity of. However, you can argue that irrespective of the elements, one has to scan through the entire vector anyway. Honestly, I don't really know how exactly they did it in the paper. Maybe they had a setup where their model was able to work with variable-sized feature vectors, and then the difficulty would simply be the length of this vector. Yeah, I don't know. Since in our setup, we assume that the length of the feature vector is constant, this was the only idea I could think of when it comes to introducing the concept of difficulty. However, maybe the number of non-zero elements is irrelevant and all of these vectors are equally as difficult. All right, and now we want to implement the PonderNet. First of all, we tell the network how many elements there are in the feature vector. Our simple step function will contain a recurrent cell. This cell takes the input features and the previous hidden state, and it outputs a new hidden state. And this parameter number of hidden just determines the hidden layer size. This parameter determines the maximum number of steps the network can ponder for, and as explained, at training time, we will actually always reach this number of steps, and we will never halt before. And related to it, we have this flag allow halting. By default, we will set it to false. However, if we activate it, then if all samples in the batch finished or halted, we don't even continue until the maximum number of steps. Okay, so what do we have inside? First of all, we have this recurrent cell that I just explained. We will use the GRU cell. However, you can use any recurrent cell you want. And yeah, as I said, this cell is responsible for coming up with new hidden states. And then we take this hidden state and we'll run it through a linear layer. In this case, it's the output layer that will turn the hidden state into a prediction. Similarly, we have another linear module, the lambda layer, which will again take the hidden state. However, it will output the halting probability. Here we store the parameters as attributes. We instantiate our GRU cell. And as discussed, we also instantiate 2 linear layers, one that is going to take the hidden state and output the y hat, the prediction, and the other one is going to take the hidden state and output the lambda, the halting probability. And of course, we will need to apply the sigmoid activation in order for the values to be in the range 0 and 1. So how does the forward pass look like? It inputs the batch of features, pretty standard, and then it returns 3 different tensors. The Y tensor is a collection of all predictions after each step. Note that the first axis of this tensor is the steps, and the second one is the samples. And this feels unusual because most of the time the batch dimension is the first one, but whatever. And of course, at training time, the first dimension will always be fixed to the maximum number of steps. However, if we allow for halting, the first dimension can end up being shorter. The second tensor that we output represents the probabilities P. It has the same shape as the Y. And if we fix a sample and then sum up across all the steps, we should get a 1 because it represents the probability distribution over different steps. And finally, we return a tensor called halting step. And this tensor stores the step for each sample where it was halted. So first of all, we extract useful attributes from the input tensor x. And here we initialize our initial hidden state to zeros. Here we initialize the tensor called unhalted probabilities. It is a helper tensor that we will update dynamically, and it stores the probability that we haven't halted yet. Here we initialize the list of p's and y's, where we will dynamically add the results after each step, and we also initialize the halting step to zeros. The minimum number of steps that a given sample can take is 1. So in a way, if a halting step is 0, it's just a temporary marker saying that a given sample hasn't halted yet. Not surprisingly, everything will happen in a for loop representing the different steps. First of all, we want to generate the halting probability lambda. If we are at the final step, it will be just once. In other words, it is certain that we will stop the forward pass. And if it's not the final step, we take our hidden state, run it through the lambda layer and through the sigmoid activation, and that will represent the probability of halting. Note that the output of sigmoid has a range of 0 and 1, so it is going to be valid. Here we took the hidden state, then ran it through the output layer, and we got a prediction, y hat. Here we don't apply the sigmoid activation because we will apply it inside of the loss function. And if the number is positive, that means that the network is predicting the parity to be 1. And if the number is negative, the network is predicting it to be 0. And we just append it to our list. And here we're just going to use the lambda that we calculated above and turn it into the probability that we hold at that given step. The difference between p and lambda is that p stands for the unconditional probability that we hold at step n, whereas the lambda stores the conditional probability, assuming that we haven't halted yet. What is the probability that we hold now? And we can actually compute the p from the lambda by just multiplying the lambda by the probability that we haven't halted yet. And here we're basically trying to determine what samples in the batch halted at this step. The formula is a little bit long, but using the computed lambda, we sample from the Bernoulli distribution. And if the lambda is high, it is way more likely that we will actually hold the process. However, this is the random part of the forward pass. The rest of the formula just makes sure we only update those samples that haven't halted yet. In other words, those are the samples that have halting step equal to 0. We already have all the outputs necessary, however, we need to prepare for the next step. Specifically, we update the unhalted probabilities, which is nothing else than taking the previous unhalted probabilities and multiplying them by 1 minus lambda. And also we generate a new hidden state using the old one and the input features. One important thing to note here is that we are always feeding the entire original feature vector into the cell, and that is why we require fixed sized input. In theory, this mapping that takes the input features and the previous hidden state and outputs a new hidden state can be as complicated as you want. For example, it could consist of another neural network that processes the feature vector element by element, allowing for variable sized feature vectors. And if we allowed for halting and all samples in our batch have already halted, then we just break out of this for loop. And again, primarily this is for the inference time. Once we are done with all the steps, we just stack up all the per step predictions and probabilities into 2 big tensors. And finally, we return all the useful tensors. All right, now let us check whether everything works as expected. So we define some parameters, and now let us instantiate the PonderNet. Let us run a forward pass on some dummy input. As expected, the shape of the predictions is 2016. 20 stands for 20 steps and 16 stands for 16 samples. P has exactly the same shape. As you can see, all entries of P are non-negative. Also, they are all smaller or equal to 1. For each sample in the batch, if we sum up the per step probabilities, we get 1. For each sample, we have a valid probability distribution. If we look at the halting step tensor, we see that there are 16 elements, and this tensor contains the information at what step a given sample was halted. Finally, let us change the allow halting flag inside of the PonderNet network. Let's rerun the forward pass. Let's look at the halting step again. We can clearly see that the maximum of all elements is 3, and since we allowed halting, we would hope that both y and p do not contain all the remaining steps, but only the first 3 steps. And as you can see, it is the case. Anyway, now the only thing left to do is to implement our loss function, and as you probably remember, it is composed of 2 different parts. The first one is the reconstruction loss. So this loss module has a single parameter, which is the actual loss function that takes the predictions and the ground truth, and it spits out a number for each sample in the batch. So we give it the probability tensor that is one of the outputs of the PonderNet, as we have just seen. We also give it the predictions of the PonderNet, and finally we also provide the ground truth labels. Note that the shape here is different than for the previous 2 tensors, and that is because we will apply this loss per each step. We return the actual loss scalar, and it is nothing else than the weighted sum of per step losses. We extract the maximum number of steps from the p tensor, and then we initialize the total loss. And here we run the for loop over steps, and for each step we compare the ground truth with the prediction, and we weigh it based on the probability distribution. And then we just simply compute the mean over the entire batch and add it to the total loss. And yeah, that is the reconstruction loss. Okay, and now let's implement the regularization loss. Alright, so as discussed before, the goal of the regularization loss is to make sure that for every sample, the predicted halting probability distribution is as similar to the geometric distribution as possible. However, the geometric distribution has one parameter that one needs to fix. And here we call the parameter lambda p, and I guess it has a nice interpretation because if you do 1 over lambda p, you get the expected value of this distribution. And we also provide the maximum number of steps. The reason why we need this is to decide on a cutoff value, because in theory, the geometric distribution has an infinite support, which means that taking, for example, 1 million steps is possible, but extremely unlikely. However, we want to have a cutoff value so that we can just turn the probability mass function into a list of floats. So here we initialize a tensor of zeros, and we want to iteratively populate it. And we will also have this helper float that we will continuously update, and it represents the probability that we haven't halted yet. So the probability of halting after k steps is nothing else than the probability that we haven't halted yet in any of the previous steps, and that on the kth step we will halt. And we will save this tensor as a buffer. If you're not familiar with buffers, it is nothing else than a tensor that we would like to store for the computation in the forward pass. However, this tensor is not trainable. Here we also instantiate the KL divergence loss. So to compute the loss, we input the p, which is one of the outputs of the PonderNet. The return value is nothing else than a scalar representing the regularization loss. We unpack the shape of our p tensor, and then we transpose it, and this way the samples are the first dimension. Here we just take the pre-computed geometric distribution tensor and we expand it across all samples. Or in other words, we just repeat the same tensor across all the samples. Finally, we compute the KL divergence, and yeah, that's the regularization loss. Let's play around with this regularization loss a little bit. So we set the lambda parameter equal to 0.5. As you probably remember, we have this buffer p underscore g that holds the probability mass function. The way you should interpret this is that the probability of halting after the first step is equal to 50%, after the second step is 25%, and so on and so on. And even though we made a cutoff after 20 steps, the weights numerically still sum up to 1. However, now let us create a new instance where the lambda is 0.2. And as you can see here, it's more probable to make more steps. And the sum is smaller than 1, so you can say that it's not a probability distribution, but again, this is just an approximation and the KL divergence computation is going to work out anyway. All right, let's write the training script. First of all, let us write an evaluation function. The goal is to run it every now and then during training to get a good idea of what is going on. Alright, so we provide a data loader that is going to stream batches of our validation set, and we also provide an instance of our PonderNet. We will return two types of metrics. The first type are just scalars, for example, the average halting step. However, we will also return tensors of metrics where we want to monitor what happens in each step. Here we prepare a couple of lists and we will be appending per batch metrics. So here we run our PonderNet. And then we use the gather operation to only extract those predictions that correspond to the halting steps. All right, so here we compute the accuracies if we were to take the predictions when the process was halted. And we also compute the average halting step. Here we disregard the halting step and we literally just compute accuracy for each step separately. And we also compute the mean probability of halting for each step. And here we just average over the batches in our validation set, and we should more or less get the metrics over the entire validation set. And now I will write two functions that take these metrics and just plot them nicely. All right, and that's it for the evaluation and plotting logic. And now let us set up a CLI. So the only positional argument is the folder where we're going to put the TensorBoard stuff. This beta float will determine how much importance we are giving to the regularization loss. The lambda p will determine uniquely the geometric distribution we are dealing with. Number of elements will determine the size of our feature vector. And as we saw, we can put a lower bound and an upper bound on the number of non-zero elements. And of course, we can also choose the maximum number of pondering steps. So here we hardcode that the number of evaluation samples is going to be 1000, and we're going to iterate through this validation set in batches of size 50. All right, so the idea here is that we are going to have multiple validation sets. One is going to be, let's say, the easy one, and the other one is going to be the hard one. And this is going to be determined by the number of non-zero elements. Here we create a TensorBoard writer and we dump all the CLI parameters as text. So here we created our training data loader. It's worth mentioning that the number of samples is the batch size times the number of iterations. And again, we are generating the samples on the fly. So this is just like a convenient setup so that we have number of iterations, gradient steps during the training. Also, if the user selected a custom range for the number of non-zero elements, we pass this information into the constructor. And now the idea is to create a bunch of evaluation data loaders so that we can understand how our model performs. So the first evaluation data loader is going to be called test, and it has exactly the same range of number of non-zero elements as the training data loader. So the second evaluation data loader is actually going to hold the easy samples. And the third evaluation data loader is going to be streaming samples that are hard. We make sure all the parameters are on the right device and have the right D-type. Here we instantiate our reconstruction loss, and the actual criterion is going to be the binary cross entropy. And here we also instantiate the regularization loss. And finally, we instantiate an optimizer, and the learning rate value is actually taken from the paper, I believe. And now we are ready to write the training loop. So we iterate through our batches in the training set, and we cast both the features and the targets to the right device and the right D-type. We run the forward pass of our PonderNet, and just a reminder, since we did not allow for halting, we will always run it for maximum number of steps. Here we compute the reconstruction loss and also the regularization loss. The overall loss is equal to the reconstruction loss plus the regularization loss times beta. We set all the gradients to 0, then we compute the gradients, and then we take the gradient descent step. Here we track the losses. However, occasionally we also want to run evaluation using our evaluation data loaders. For each of the data loaders, we run the evaluate function that we prepared at the beginning of the script. And here we created the two plots and we tracked them with TensorBoard. And since we also have a bunch of single scalar metrics, we just track them with TensorBoard too. And when the evaluation is done, we also store the model, overriding any previous checkpoints. And that is it for the training script. Okay, so we are going to run two different experiments. First of all, the paper discusses how sensitive the results are on the hyperparameter lambda p that uniquely identifies the target geometric distribution. Here we just create a grid of 5 different lambdas and run the training for each of them. And also note that we are setting number of elements equal to 15, which is very small compared to the paper. However, this will enable us to get some results relatively quickly. Here you can see the second experiment, and the goal here is to assess the model's ability to extrapolate. The input feature vectors will have 30 elements. However, at training time, the maximum number of non-zero elements will be 25. Our goal is to investigate how the model performs when we give it vectors that have 26, 27, 28, 29, and 30 non-zero elements. Let's look at the results of the first experiment. Here we see the overall loss, and as you can see, something went wrong for lambdas 0.5, 0.7, and 0.9 because the training was interrupted. I didn't really check the root cause of the problem, but I believe it has something to do with nonce or infinities. Even in the paper, authors show that for lambdas higher than 0.5, the results are, let's say, unstable. I guess the main reason here is that we are forcing the PonderNet to take 2 steps or even fewer steps on average, and it just doesn't like it. Anyway, for runs where the lambda was smaller than 0.5, the loss was going down. Let me deselect the failed runs. So the overall loss, as you have seen, is composed of two components, the reconstruction loss and the regularization loss. And here you can see the reconstruction loss evolution over the training. And we see that at the beginning, it's constant, and then it starts to decrease drastically. If we look at the regularization loss, we see that it starts to decrease immediately and the loss is very low. However, then it radically increases and finally it slowly decreases for the rest of the training. This behavior of the reconstruction loss is something I observed in all experiments, and it shows that the network tries to match the target geometric distribution perfectly at the very beginning, and only then it starts to pay more attention to the reconstruction loss and is less strict about the predicted distribution P. Looking at the accuracy of the halted predictions, we see that we are able to reach almost 100% accuracy. Here we see the average halting step. The expected value of halting steps should be 1 over lambda if we match the target distribution perfectly. We can also look at the halting step in cases when we only evaluate on simple samples. And in this case, those are the samples that have between 1 and 4 non-zero elements. So as you can see, let's say we have 10 steps for lambda 0.1 and 6 steps for lambda 0.3. And if you look at the average halting step for hard samples, or in other words, samples that had between 11 and 15 non-zero elements, and we see that on average, the network takes more than 1 step more on the harder samples than on the simple ones. And this is consistent with our mission, let's say, of making the PonderNet spend more time on the harder samples. Let us now look at some plots. Here you can see the target geometric distribution in red color and the predicted distribution at the end of the training in green color. They are very similar. However, for the predicted distribution, it is close to impossible to hold before the step number 5. By the way, let me show you how this plot evolved over the training. Alright, so right after initialization, we see that the predicted distribution is behaving more or less like a geometric distribution with lambda equal to 0.5. That is because a randomly initialized linear model will predict zeros on average. However, after a few steps, you can see that we are pretty much able to match the target geometric distribution. However, as we saw in the regularization loss evolution, the network then starts focusing more on the reconstruction loss and mostly defaults to taking the maximum number of steps. And it is only from now onwards that we are starting to approach the target geometric distribution. For lambda 0.3, the evolution is similar, and this is the final predicted distribution. Finally, if you look at the average prediction, let's say for lambda equal to 0.3, when we give the network easy samples, we see that the most likely halting step is around 4. However, if you look at the harder samples, we see that the most likely number of steps is 5, and the distribution is definitely shifted towards more steps. And again, we can make the same conclusion, and that is that the PonderNet takes more steps when the input sample is more difficult. Here we see the accuracy of the predictions if we disregarded the halting and always evaluated just one specific step. And we see that around the step 6, we hit the 100% accuracy, and it is consistent with the average halting step. The network halts when it knows that the maximum accuracy has been reached. What is also cool is that the accuracy does not degrade if we take further steps. All right, now we will check out the results of the second experiment. In terms of the loss, you can see that it is very close to 0. Also, it is worth noting that in this experiment, the input features have 30 elements, which made the training way longer. Here is the accuracy evolution on samples from 1 to 25 non-zero elements. Exactly the same setup we had in training. And not surprisingly, we are able to get almost 100% accuracy. Here we see the accuracy for samples with 26 to 30 non-zero elements. Quite amazingly, the network is able to get around 95% of them right. This shows that the PonderNet is able to generalize. For the easy samples that we have seen during the training, the average halting step is around 8. When it comes to the hard samples that were not seen during the training, the network takes around 9 steps on average, which is at least 1 step more than on the easy samples. And again, this supports our hypothesis that the PonderNet is able to adjust to the input difficulty and think longer when it's really necessary. If you look at the plot, it tells us the same story. So for the easy samples, we see that the step number 4 has the highest probability. And if we look at the hard samples, we see that the step 6 is the one with the highest probability. And what is also interesting is that sometimes the PonderNet gives itself the luxury to think for maximum number of steps. However, maybe this behavior would disappear if we train the network for more iterations. Anyway, that is it for the video. I have to admit that I really enjoyed this paper and preparing all the code and experiments. I find the idea pretty original, and especially the fact that the network can dynamically modify its forward pass. I hope there will be more research and future work on this topic, and that we will have some drop-in implementations that just take a standard supervised neural network and then wrap it in this pondering logic. Anyway, all credits go to the authors of the paper and the people at lambdas AI. Also note that the experiments that I ran in this video were not supposed to reproduce what was done in the paper, and it was mostly just me playing around and coming up with different ideas. Thank you for making it to the very end. You are awesome, and as always, I will be happy to get any feedback here on YouTube or other platforms. Have a nice rest of the day, and see you next time.